Question 1a. A research nuclear reactor is designed to produce a beam of neutrons. The neutrons are produced by the fission of uranium, one of several possible reactions being described by the following equation. Neutron and uranium-235, resulting in barium-141, krypton-92, and 3 neutrons. The neutrons released in these reactions have a wide range of energies, but can be slowed down by passing them to material of similar nuclear mass to form a beam of slow neutrons. Use the concept of binding energy to explain why fission reactions occur. Average binding energy per nucleon is the average amount of energy required to separate one nucleon from a nucleus. A higher average binding energy per nucleon means that more energy is required to separate a nucleon from a nucleus, and thus is more stable. The average binding energy per nucleon rises to a peak at around iron 56 and slowly decreases. Uranium-235 is near the end of the curve, and thus has a lower binding energy per nucleon than elements such as barium-141 and krypton-92. Therefore, it is energetically favorable for element of high mass to undergo fission, as the daughter particles are more stable and energy is released in the process. Question 1b. Particles such as neutrons also behave as if they have a wavelength, given by lambda equals h over p, where h is Planck's constant and p is the momentum of the particle. Show that the wavelength of a slow neutron with a kinetic energy of 0.0400 electron volts is 1.43 times 10 to the negative 10 meters. Converting electron volts to joules, we get 6.40 times 10 to the negative 21. We know that kinetic energy equals half times mass times velocity squared. Rearranging this and solving for velocity, we get 2,769 meters per second. Momentum equals mass times acceleration. Substituting our numbers in, we get the momentum of the neutron is equal to 4.62 times 10 to the negative 24 kilogram meter per second. Substituting into lambda equals h over p, we get the wavelength of the neutron is equal to 1.43 times 10 to the negative 10 meters. Question 1c. Neutrons of energy 0.0400 electron volts can diffract from planes of atoms in crystalline copper of spacing d equals 2.20 times 10 to the negative 10 meters, as shown below. By first considering the path difference for neutrons scattered from adjacent planes, show that a diffraction peak will be observed at angle theta equals 19.0 degrees. The path difference in this case is equal to d sine theta plus d sine theta, which is 2d sine theta. At diffraction peak, the path difference is equal to 1 lambda. Hence, 2d sine theta equals lambda. Rearranging and solving for sine theta, we get sine theta equals 0.326. Solving for theta by taking the inverse sine of both sides, we get 19.0 degrees, which is what we're trying to find. Question 1di. Neutrons have mass but zero charge. A neutron with kinetic energy of 0.0400 electron volts is initially traveling horizontally. Calculate the vertical deflection of the neutron due to gravity as it travels a horizontal distance of 1.00 times 10 to the 2 meters. In question 1, we found that the velocity equals 2,769 meters per second. We know that velocity equals displacement over time. This means that time equals displacement over velocity. Substituting our numbers in, we get the time to travel 100 meters horizontally is 0.0361 seconds. We can use the equation displacement equals initial velocity times time plus half times acceleration times time squared to find the vertical deflection of a neutron. Since the neutron is initially traveling horizontally, there is no initial vertical velocity. Thus, displacement equals half times acceleration times time squared. Substituting our numbers in, we get the vertical deflection of the neutron due to gravity as it travels a horizontal distance of 1.00 times 10 to the 2 is 6.40 times 10 to the negative 3. Question dii. Explain whether or not a uniform electric field can be used to compensate for the effect of gravity on the neutron. No. Electric fields produce a force that is equal to electric field strength times charge. Since neutrons are neutral, their charge equals 0. Thus, force is 0. Therefore, the electric field will have no effect on the neutron and will not be able to compensate for the effect of gravity on the neutron.